Hi everyone, we are from Group 11 and my team members Ananya and Beena will be joining me today to give the presentation on paper Points to Analysis for Java using Annotated Constraints. To start it, here the main goal of the paper is to determine set of objects pointed by reference variable or a reference variable object. So here we are using constraint based approach because it models precisely and efficiently the semantics of virtual calls. So as we mentioned in the paper, the compiler tech is used for making Java a viable resource for production strength software. This is because the runtime behavior and the fundamental static analysis is based on point analysis. So as we mentioned, the goal of the paper is to set the objects are stored in reference variable of the object field. So here the point analysis leads to other type of analysis which are like side effect, definition, usage, which are used in optimization of code. And the point analysis is a prerequisite for all this type of analysis, and it is also involved in optimizing the code and virtual call resolution, removal of unwanted errors, synchronization, and storage based allocations. So the paper introduces constraint annotation and shows how the analysis is done using annotation inclusion constraints. So the annotation plays an important role in analysis, and here we are using two types of annotation such as method annotation and field annotation. When coming to the method annotation, it is used in model precisely the semantics of a virtual call, target object, receiving object and target method. Whereas when coming to the field annotation, it is used separately and it is used for tracking the flow values through different fields of an object. By using these techniques, it is able to achieve the practical and precise point of analysis in Java. Java contains large amount of unused library code in the actual program. When coming to the Anderson analysis, considering this as an actual code and executing the program can be a major drawback because it can affect the cost and the precision of the analysis. So that is a major drawback of Anderson's analysis. And when coming to the point analysis, it can be a lot better, and that is not the case here because the code is kept track from the starting point itself, and that is a major advantage for the point analysis. And out of 23 programs, 16 are having analysis time less than a minute, and that keeps point analysis at the top. And if they are having a large Java programs, they run for few minutes and uses less than 180 MB of the actual memory. And according to this paper, a good analysis or precision is obtained when determining which object can read or write written program statements. So and also the tests show that the point analysis can be used to detect many objects that don't need synchronization and can be stacked rather than heap allocated. And also client uses side effect analysis, definition usage analysis, and dependency analysis require this object read write information. Further sum, that is why the tests are also showing a lot of positive sides. The contributions of the paper are: first, the general purpose point to analysis is mentioned with the Anderson's points of analysis for C, while the next, the constraint based approach is defined with point analysis for Java. The second contribution is the analysis of large Java programs, which show the analysis run is practical and space and has closest information of the read write data. It has also a significant improvement in the precision of the program called call graph. The figure here shows the points to graph, and it represents how it is obtained by computing points of set for variables and fields, which is the analysis, and it is typically represented by one or more points of two graphs. Here set R represents the reference values, set O represents the name of all objects created by the object allocation sites, and set F contains all instances fields in program classes. Here the analysis semantics is expressed as a manipulation of points to graph containing two kinds of edges. While the first edge shows the reference variable small r points to the object OI, and the other edge shows that field small f of object OI points to the object OJ. A sample program, and as here mentioned, this is the points to graph, and it simplifies the presentation, and in the paper it only discusses the kinds of statements listed below. Here the direct assignment 1 equal to r instant field. Here the direct assignment 1 equal to r and instant field is written to 1.f equal to r. Instant field read 1 equal to r.f, whereas the object creation is represented by 1 equal to new c. The virtual innovation 1 equal to r0.m multiplied with r1 to rk. At a virtual call name m uniquely identifies a method in the program, the compile time target of the call, and it is determined based on the declared type of r0. At runtime, the invoked method is determined by examining the class of the receiver object and finding the first method that matches the signature and return type of m. So coming to the applications of points to analysis for Java. So using points to analysis, the main application is optimizing compilers and software engineering tools. For it has very many advantages. So the cost of analysis can be amortized across many clients. Once implemented, the analysis can be reused by various clients at no additional development cost. Such reusability is an important practical advantage. Here in this section, session, we are discussing about different type of analysis for Java, like object read-write information, for example. Here, in the points of analysis can be used to determine which objects can read or write given program statement. So that is the major advantage, and this information is necessary for many and it is a prerequisite for variety of other analyses. And analysis that require read and write information are used in compilers to perform various optimizations such as code optimization, partial redundancy elimination, and so on. And in addition to this, analysis play an important role in variety of software engineering tools, and this is the reason it has a practical and precise point of analysis is crucial for enabling such type of analysis and for optimization purposes. So the next advantage is call graph construction and virtual call resolution. The points to analysis can be used to determine the target methods of a virtual call by examining the classes and also possible receiver objects. So the call graph have the analyzed program. This graph is also a prerequisite for interprocedural analysis. If the call only has one target process, it can be handled by replacing the virtual call with a direct call, which reduces the virtual dispatch runtime overhead. Furthermore, the virtual call resolution also allows for subsequent inlining of the target process, theoretically allowing for additional caller optimizations. The next advantage is a synchronization removal. Synchronization in Java allows safe access to shared objects in multi-threaded programs. Synchronization operations on locks can have a considerable amount of time overhead. This overhead can occur even in a single-threaded program. Because of this, Java libraries are written in a thread-safe manner. Static analysis can be used to detect properties that allow removal of unnecessary synchronization. Point to analysis can be used in this case as an alternative to escape analysis in detecting thread local objects. Even an object, and suppose that in the points of graph computed by the analysis is not reachable from static or object classes that implement the interface. It can be proven from this case that even the thread that created it, we can identify such thread local objects by performing a reachability and computation on the points of graph. This approach is similar to multi-threaded object analysis. Coming to the next advantage, stack allocation is an object that can be allocated on method stack from rather than on the heap. In certain instances, rather than allocating an object may be allocated on the stack on a frame of process. The transition lower garbage collection overhead while still allowing for other optimization including an object reduction. Static analysis including synchronization elimination can be used in finding properties that allow stack-based allocation. So, some escape analysis can detect method local objects. Clearly, such objects can be allocated on the stack frames of their creating methods. Point to analysis in this case can be used as an alternative escape to analysis in identifying method local objects. So that is the main advantages for using the point analysis. In this slide, we will be discussing about the points to analysis for Java using annotated constraints. In the previous analysis, we defined the terms set R to all reference variables and set O to the names for all objects created for object allocation. Every element R union O essentially an abstract memory location representing a set of runtime memory locations. Here we generally approach the modeling of Anderson's, which is not using a non-annotated constraint. For each abstract location X, a set variable Vx represents the set of abstract location pointed by X.
Moving on to the next slide, constraint for assignment statements. The first two generation rules are straightforward. The rule for L dot f equal to R uses the first constraint to access the points to set of L, and the second constraint to update the values of field f in all objects pointed to by L. After processing the statements, our analysis creates the following constraints. These are shown here, and where u and w are the fresh variables. For the condition tau of u less than tau of w, we consider p dot f equal to q, and since we have this equation, we can use the trans rule and the resolution rules. Vq subset are equal to with respect to f, and u subset are equal to v01. Handling of virtual calls. For every virtual call in the program, our analysis generates a constraint according to the following rule shown here, and this rule is based on the lambda, which is a constructor, and the annotation of the constraint is one of a kind identifier for the call's compile time target method. This is an annotation which is used to find all the acceptable runtime goal methods during the study. To carry out the virtual dispatch on all receiver objects which is pointed by R0, we use a pre-computed lookup table to make this process go as quickly as possible. Here, given the class of the receiver object and the unique identifier from the compile time target of the virtual call, the lookup table returns a lambda term of the form with the equation. Here, pi are the formal parameters of the runtime target method, and p0 corresponds to the implicit parameter. To model the effects of virtual calls, we define an additional closure rule called the virtual. Virtual is applied whenever we have two constraints of the form as shown here, and the edge from the reference term is a predecessor edge and the edge to the lamb term is a successor edge. Whenever two such constraints are detected, the lookup table is used to find the lambda term for the runtime method corresponding to the object O and the compile time target method M. The result of the applying virtual are two new constraints which are obtained as shown here. Cycle elimination. What is cycle elimination? Cycle elimination is a technique that can be used to reduce the cost of Anderson's analysis for C. Here we have adapted this technique to allow us to reduce the cost of our points to analysis for Java. The idea behind cycle elimination is to detect a set of variables that form a cycle in the constraint graph, and this is represented here in this following equation. Whenever a cycle is detected during the resolution process, one variable from the cycle is chosen as a witness variable and the rest of the variables are redirected to the witness. This transformation has no effect on the computed solution but can significantly reduce the cost of analysis. And this cycle detection is performed every time a new edge is added between two variables which are Vi and Vj. Cycle detection is just partial because not all cycles are detected. Here we use a limited form of the cycle elimination to ensure the correctness of our Java review. Projection merging. It is also a technique which is used to reduce the cost of Anderson analysis for C, and this is also a technique for reducing the redundant edge additions in constraint systems. It combines multiple projection constraints for the same variable into a single projection constraint. For example, constraints V subset are equal to projection Ci u1 and V subset are equal to projection of Ci u2 are replaced by this equation as shown here. Here W is a special projection variable, and for points to analysis for C, constraints of the form W subset are equal to Ui are represented only as an successor edges. This restriction guarantees a bound on the number of projection variables W. Cycle removal does not deal with projection merging in our annotated constraint structures. For Java, the decoupled form of projection merging has a major impact on the analysis running time. Tracking reachable methods. We also enhanced our research to keep track of reachable methods in order to avoid analyzing dead code, since Java programs heavily use libraries that contain many unused methods. As a result, we only consider the effects of statements in a process body if the method has been shown to be reachable from one of the program's entry methods. The set of entry methods contain the main method of the starting class, the methods invoked at JVM startup, for example, initialize system class, the class initialization methods containing the initializers for the static fields. And a call to constructor is followed by a call to appropriate finalize process. A call to thread.start is needed for the multi-threaded programs. Coming to the analysis implementation and empirical results. To process Java bytecode and create a typed intermediate representation, we use the suite framework, which is www.sable.mcgill.ca, which is of the version shown here, and Berkeley Analysis Engine is used for the constraint based analysis. BAN is a collection of tools for creating software analysis based on constraints. This analysis works on top of the constraint engine by processing newly discovered reachable methods and generating the appropriate constraints. All the tests here run on the Sun Ultra 60 computer with a clock speed of 360 mHz and 512 MB of physical memory. The times given are the averages of the 3 runs. Here we use 23 public available data programs with bytecode size ranging from 56 KB to around 1 MB. We also used programs from SPEC JVM 98 suite as well as benchmarks from previous work on Java research and programs from an internet archive of popular public available Java applications. Moving on to the next slide, this table represents the characteristics of the data programs. Here, the first left column represents a program, and the number of users, which are the non-library classes, and their bytecode size are shown in the first 2 columns. After using the CHA, which is called the class hierarchy analysis, which is used to root out irrelevant classes and methods. The next 3 columns display the scale of the program, including the library classes. The last column shows the number of statements in the suite's intermediate representation.
After implementing the points to analysis using annotated incursion constraints, now we measure a set of experiments for the cost of analysis. These experiments were run on 16 out of 23 programs, and this took less than a minute. The table shown in the next slide has the record of data, and the first 2 columns of this are running time of the analysis and the amount of the memory used. For all the programs to run, the running time is less than 6 minutes and memory usage is 180 MB. Here our results are very practical in terms of running time and memory usage,
as evidenced on a large set of programs. This practicality means that the analysis can be used as a relatively precise general purpose points to analysis for advanced static compilers and software engineering tools for Java. Analysis costs can be reduced further if the library code is analyzed in advance. That means to allow certain partial analysis information about the Java libraries to be computed once and subsequently used multiple times for different client programs. We intended to investigate this approach to our future work. We also investigated a version of analysis in which no field annotations are used and therefore individual object fields are not distinguished. The table here represents running time and memory usage of the analysis with and without fields. Here the first two columns are for field version, and the last two columns are time and memory of no field versions. The running time is between 88% and 12056%, that is with an average of 892% and median of 384% of the running time of the original analysis. Typically, as we can see, no field versions is significantly more expensive, and for one of the large program it even ran out of memory. These results shows why we need to distinguish between object fields, which in turn reduces analysis cost. By using field annotations, we have been able to distinguish object fields in a simple and efficient manner. Here we have performed measurements to estimate the potential impact of our analysis on clients of object read write information. Here the analyses used are like side effect analysis and diffuse analysis. After carefully considering all the expressions occurring in the statements which are reachable methods, the points to set containing all objects that may be read or written is applied. And the more precise points to analysis produce small number of accessed objects. This has helped to improve the precision and reduce the cost of the clients of the read-write information. Thus, to estimate the potential impact of our analysis, we measured the number of accessed objects for each indirect access expression. Similar metrics have been traditionally used for point analysis for C. Here the table shows the distribution of number of accessed objects, and each column corresponds to a specific range of numbers. For example, the first column corresponds to expressions that may have only accessed a single object, while the last column corresponds to an expression that may have accessed 10 or more objects. Each column shows the percentage of all indirect access expressions corresponds to a particular range of number of accessed objects. Here, the measurements in Table 3 indicate that our analysis produced precise read-write information. Typically, more than half of the indirect access are resolved to a single object, and an average of 81% of the access are resolved to at most 3 objects. And these results show that the analysis is promising candidate for producing useful read-write information for clients such as aggressive optimizing compilers, in which optimizations require precise read-write information, and also for software engineering tools in which precision is important because to reduce the human effort spent on program understanding, restrictions, and testing. For our next application, that is call graph construction and virtual call resolution, we have compared our points to analysis with rapid type analysis, that is RTA, which is used widely for call graph construction analysis. It performed a reachability computation on the call graph generated by the CHA. RTA computes a more precise call graph than CHA. Both our analysis and RTA improve the call graph computed by the CHA by identifying set of methods reachable from the entry points of the program. This reachability computation reduces the number of nodes in the call graph. We summarize this reduction without explicitly showing the number of nodes for each program, and an average, reduction in the number of nodes is 54% for our analysis and 47% for RTA. On average, call graph is computed for analysis as 14% less nodes than the call graph compared by RTA. This reduction allows subsequent analysis and optimizations to save ignored portions of the program. Here in the table, the first section shows the average differences, and the second section of the table shows the percentage of call sites that were resolved to a single target method. Here, the pointer analysis performed significantly better than RTA. On average, 53% and 50% of the virtual call sites are resolved. This increased precision allowed better removal of runtime virtual dispatch and additional method inlining. That is, on average, analysis removed more than twice as many targets as RTA, and this improved precision is very beneficial for reducing the cost and improving the precision of subsequent inter-procedural analysis. Here, to determine the improvement for call graph edges, we considered call sites that could not be resolved into a single target method by CHA. And let V be the set of all CHA unresolved call sites that occurred in the methods identified by an analysis as reachable. Here for the data programs, the size of V is between 7% and 44%, that is an average of 22% of all virtual call sites in reachable methods. For each site of V, we have calculated the number of target methods according to CHA and the number of target methods according to RTA. And the results showed that on average, our analysis removed more than twice as many targets as RTA, and this improved precision is obviously very beneficial for the cost and also for improving the precision of subsequent interprocedural analysis. Here in the table, the total number of invocations of CHA unresolved call sites are shown, and also the number is an indicator of the runtime overhead of virtual dispatch as well as the missed opportunities for performance improvement through inlining. Here, the percentage of total number which was contributed for call sites by RTA was also measured. These percentages are shown in the column B. Higher percentages indicate higher potential for performance improvement. The results from this experiment indicate that RTA has little potential for improving than the runtime performance over CHA. Analysis also significantly showed higher potential, and for several programs it allows the resolution of the majority of runtime virtual calls. In addition, this profile is also used to determine CHA unresolved call sites and for one runtime target. Column C shows the contribution of such sites to the total count from column A. This number is the upper bound on the number of invocations that could be resolved by static analysis. By comparing column B and C, it is clear that in many cases, our analysis performance close to the best possible performance. Our last application for pointer analysis in this paper is synchronization removal and stack allocation. To investigate the impact of our analysis on synchronization removal and stack allocation, we identified all object allocation sites that correspond to thread local and method local objects. Across all programs, the analysis detects a significant number of allocation sites for thread local objects. On average, about 48% of all allocation sites have been found to be thread local objects. These results indicate that the points to information can be useful in detecting and eliminating unnecessary synchronization in Java programs. The analysis also discovered a significant number of sites for method local objects and average 28% of all sites. These results suggest that there are many opportunities for stack-based allocation that can be detected with our analysis. As in the figure, this shows what percentage of allocation sites in reachable methods were identified as thread local or method local. With virtual call resolution, additional profiling experiments were performed to obtain better estimates of the potential impact on runtime performance. Using the same set of programs with instrumented user classes and the same data inputs, the number of runtime objects created at each object allocation sites were measured. Here in the table, the first column shows the created objects and the other two columns showed what percentage of these objects were identified by our analysis as thread local or method local. The results from this experiment indicate that analysis has good potential for improving the runtime performance through synchronization removal and stack-based object allocations. These results are also similar to the results obtained through more expensive flow and context-sensitive escape analysis. Even though directed comparison with this previous work is not possible, the results suggest that our analysis may be viably alternative to this more expensive analysis. Here we have described the pointer analysis for Java based on Anderson's pointer analysis for C. A constraint-based approach with constraint annotations was carried out in this research. Many tests were performed on Java programs, showing the cost of study is reasonable. Also, the point to solution affects object reader information, call graph creation, virtual call resolution, synchronization removal, and stack-based object allocation. Our findings show that the study is a viable candidate for a reasonably accurate, functional, all-purpose pointer analysis for advanced Java optimizing compilers and also software engineering tools. Thank you.